For the second talk, the orator is Hein Putter, so from Leiden University Medical Center, and we please talk about the landmark approach.
Thank you very much. It's a pleasure as always to be in Bordeaux. Also my favorite city in France. Okay. I will talk about landmarking and about landmarking for dynamic prediction in particular, and very particularly about also landmarking and competing risks. So the first half of my story will be about dynamic prediction and landmarking in overall survival context. And then after half an hour or so, I will come to the other part, landmarking and competing risks. So first I will give you a little bit of background. Thomas has already mentioned landmarking. I will give you a little bit of historical background where the term landmarking comes from and where the terminology comes from. And then say a little bit about dynamic prediction. Why dynamic prediction? I don't have to explain this to you, but how these connect later on. Okay, so the origin of the word landmarking, at least, maybe not the method landmarking, but certainly the word and the term landmarking, is from a paper in the very first issue of what is now one of the major oncological journals, the Journal of Clinical Oncology. It's the first issue. It was a paper by Anderson, King, and Gelber in 1983, and it had to do with the debate that was going on at the time, how to analyze a situation where you want to analyze the effect, quantify the effect of response to chemotherapy on overall survival in cancer patients. And to put it bluntly, chemotherapy is given to cancer patients to make the tumor smaller. If that happens, that's called response. There's actually something like a partial and complete response, but I will not go into the details of that. So you can have a response, and that usually takes some time. It takes maybe 6 months or so, to become apparent whether the chemotherapy is working, whether you have a response, yes or no. And so the common way of analyzing this problem, whether the response to chemotherapy has an effect on survival, was to make two groups. One of the groups is the people that responded to the chemotherapy, and the other group is the people that did not respond to the chemotherapy. And then you simply compare the survival between these two groups. And there is a problem with this approach, more problems with this approach, but the most important one is perhaps that if you consider a potential responder, if there's such a thing as a potential responder, this person who will respond to the chemotherapy given the chance, that person in that analysis will only belong to the responder group if this person survives to really experience the response. If the person dies before the response takes place, this person will be in the non-responder group because the response was not observed because the person died. So a potential responder will only belong to the response group if he lives long enough. And that's not true for a non-responder. A non-responder will always belong to the non-responder. Also if the person dies very quickly. So the comparison is not fair. In some sense you could say that the people in the responder group are immortal for some time. They are immortal for the time until their response occurs. And that's what the epidemiologists call the immortal time bias. So this is a biased approach, and this paper dealt with this bias that could occur. And this problem actually comes in a great number of disguises actually. And I'm sure people who are working in survival analysis have come across this in one sense or another. For instance, the effect of recurrence on survival. People who have a recurrence will live longer because they have to be alive to experience the effect of transplant failure on survival in transplant studies, effect of compliance on recurrence, effect of drug-specific adverse events on recurrence is also something that's studied nowadays in the cancer literature. It appears that if the drug is doing something, it is doing something to the cancer, something good, but at the same time, it's very active. It's also doing something bad at the same time. So it's also causing side effects. So for people who get more side effects, that's a sign that the drug is doing something, and they have actually a better drug. This is an interesting one. I always use this for teaching purposes. The effect of winning an Oscar on survival. It was a paper by, I think it's 1983, in the Annals of Internal Medicine by Redelmeier. I'm not sure if I have the reference, otherwise you can ask me. Comparing lots of academic American actors and comparing how long they lived. And it appeared that people who won an Oscar in their career lived longer than the people who were also actors and did not win an Oscar. And of course it's not true. The explanation that they give originally was that this was something psychological. You're in a winning mood and nice effects appear and you live longer. And of course it's not that, it's the other way around. And you have to be alive to be able to win an Oscar. So the people who win an Oscar have managed to stay alive for a long time. So that's and a couple of years later, the correct analysis appeared, and there's no effect of winning an Oscar. It doesn't make you live longer. Even now, a couple of years ago, there was a very similar. People who win the Nobel Prize, well, they're also very old when they get the Nobel Prize. They also live longer than other scientists. So, unfortunately, the incorrect approach of making this comparison at the beginning, as if it were already there at the beginning, is still prevalent in medical journals. Sometimes when I give a talk like this, I look up the latest issue of the major journals, and I always manage to find an example. I can do this here, but it's very prevalent. This mistake is made very often. And the crucial issue, of course, is that responder versus non-responder is not something that is already determined from the outset. I mean, it takes time to observe whether you are responding, yes or no. And we all learn that when studying survival and comparing groups, you should not make groups based on something that is to happen in the future. So there are two alternatives that have been proposed, or maybe there are more actually, but two alternatives also discussed in that paper. One is the which is very commonly used, the time-dependent covariate. So as long as you acknowledge that the response to chemotherapy is something that depends on time, in the beginning you're a non-responder, and after some time you will become a responder. So the covariate that you are looking at is actually time-dependent covariate. Then you can do a time-dependent approximation, and then you look at the correct answer. And the other, and that's where this paper was a landmark paper in that sense, was to use a landmark method. And the landmark method uses a slightly different approach of dealing with this. It's sort of you separate the past and the future. This is why it goes wrong is that you somehow the future of the response is entangled with the future of the event. And if you disentangle those, also your problem is solved. So you take a landmark time point, some point after the beginning, maybe 6 months or so, and then you use your groups based on everything that has happened in the first 6 months, and then you use the further follow-up for evaluating your outcome, your survival. So that is called the landmark. You define a landmark time point, very often it's, in this context I would say maybe 6 months or so. Then you define the groups based on everything before the 6 months, and you evaluate after 6 months. And that means that you have to remove the patients who have already had an event within the first 6 months. They have to be removed from the landmark analysis. Okay, so that's a little bit about the history of landmarking. That's where the term landmarking comes from. And now, a little bit by dynamic prediction. This slide is not needed for you. You know how important dynamic prediction is, because otherwise you wouldn't be here. Maybe I can use it to make a plea that also we should try more to get this dynamic prediction into the medical field. I mean, there's a lot of papers about dynamic prediction in the statistical field, but I think Carol mentioned thousands of prediction models in the medical field. There are certainly not thousands of dynamic prediction models. In fact, I don't know of any actually. There may be some, but it's very rare. And I think there could be a lot more dissemination of this in the medical field. Okay. I want to illustrate the use of landmarking, how you can use landmarking, this idea that it's actually meant to estimate an effect of something, was originally introduced for estimation purposes, not for prediction purposes. I want to show you how you can also use landmarking for prediction purposes, for dynamic prediction in particular. And to illustrate this, I'm going to use not a cancer example, but an example with something that all of you can relate to, which is just being alive, living. This is from the US Health and Retirement Study. It's the Health and Retirement Study is a number of nationally, that's in the US, nationally represented cohorts. A number of them, in this illustration, I use only the oldest cohort because I'm interested in how long people live at old age. So this is a cohort which is already a separate cohort called the AHEAD cohort. People born before 1923 and aged 70 and older in 1993. And from 1993 on, they were regularly followed up. And the outcome of interest is overall survival. I just want to know how old do these people get. And the time scale is also age, the age of the person. I want to say something like, what is the probability that someone will become 90 years of age or 100 years? There's some time fixed covariates that I will be using. That's gender, that's certainly time fixed. Education, also reasonably time fixed. BMI is actually not time fixed. The smoking is also not time fixed, but that's the information I have is only from the time of entry into the study. So I don't have this BMI regularly updated. That's a topic for tomorrow, I would say. And I don't have the information here. So I treat this knowing that it's actually a time-dependent covariate. The value will change over time, but I don't have the information, so it's time-fixed covariate in my example. I do have one time-dependent covariate, and that's an ADL score. It's a 0-1 covariate saying that a person, according to some definition, is disabled or not. This is a very often used scale, especially in research in older people. Basic activities of daily living, it's 5 or 6 scales: walking, bathing, dressing, toileting, feeding, things we all do every day. And as soon as you answer with difficulty or impossible for at least one of those items, then that's the definition, and you are, this definition, ADL disabled. So, you're either healthy, not disabled, or you are disabled according to this definition. And that changes over time. You can become disabled, and you can also recover from disability. And the objective is dynamic prediction of survival of at least 10 years beyond a certain age. Thomas made a nice distinction. You have 2 time scales. You have the time point at which you do your prediction. The time point at which I do the prediction is a certain age. It's not only. Oh, yeah. Okay, anyway, I'll continue. The time scale at which you do your prediction is the age of the patient, for instance, of the individual, actually, not necessarily patient. For instance, at age 80, at age 80, for instance, I want to predict, the second time scale, 10 years ahead, what's the probability that this person will still be alive 10 years later, 10 years from now. So, if the individual is age 80, I want to know what is the probability that the person is still alive at age 90. So 10 years ahead, that's my horizon. And then given the disability status of that individual at that time, and also given other covariates like gender. So these are the covariates. It's gender. You see that this is already a quite older population, so the majority, slightly more, is female already. Education is less than high school, college. BMI at entry, should repeat, and smoking, never smokers, past smokers, and current smokers. Those are the covariates that I want to consider in my prediction. So one of the ways that you could use to do the dynamic prediction in this context is to use a multi-state model. And that multi-state model would then distinguish between the 2 states, healthy and disabled, And you could go back and forth between healthy and disabled. You start at healthy, and then you become disabled, and then you can become healthy again. And you go back and forth from these states. And then from either of these states, you can then die. So those are the states. And what you can do this is called a reversible illness-death model. It's an illness-death model. This is the healthy, this is the illness state, this is the death state. And it's reversible because you can go back and forth between the healthy and illness states. And then you can, what you would do in a multi-state model is model the transitions from one state to another using a box model or whatever. And within this multi-state model, within this formulation, you will have certain values of your covariates. Set star, that's sort of indicating a new individual, a certain individual. And then this would say that at this point in time, at this age, the person is either healthy or the person is disabled. X. And then for this person, I want to know what is the probability that at some horizon, 10 years later, for instance, the person is either healthy or disabled, so still alive. Okay, that's the translation of my dynamic prediction probability in terms of this multi-state model. Okay, and then what you would do in multi-state models, you would make models for the transition intensities. So we've got 4 transitions, one from healthy to disabled, one back, and 2 transition to the death state. You would make models for each of these transitions, and after having done that, you could use some calculations to calculate the probabilities that you want. I'm not going into that. Just to say that if the Markov assumption holds, the Markov assumption says that if you are somewhere, the future will not depend on what has happened to you before that, but really depends on the present. If in that lucky situation, there are no easy closed form expressions, but at least you can calculate the probabilities that you want. Otherwise, if the Markov assumption does not hold, you basically are in some trouble. You would have to do simulation. Although it's not that bad, you would only need one of the computers of the weatherman that Carmen showed, not the whole part. Anyway, but then you would have to do simulations. And actually in our data there's evidence that the Markov assumption does not hold. I mean, if you look at the picture here, answer this one. People who have been disabled before and are in the healthy state, they have a higher probability of becoming disabled again. So there is either some memory or maybe some frailty going on that if you have been disabled before, you're more likely to become disabled again compared to people who have not been disabled before. So that's the violation of the Markov assumption. So the Markov assumption is probably not true here. So there is no easy solution of obtaining dynamic predictions to this context. So, but there is something rather easy that you can do instead, and that's to use landmarking. So I talked about landmarking, about dynamic prediction. Now dynamic prediction for landmarking. This has been proposed by Hans van Ouwering in a paper in 2007 in the Scandinavian Journal of Statistics. And the idea is actually amazingly simple. So suppose that I want to have someone of age 80, maybe a female, that doesn't really matter, so, and I want to estimate the probability for someone who's alive at age 80, the probability that this person will live to be 90 years of age. Well, in an ideal situation, I would have an enormous database of all the people alive, and of all the people, how long they survived, etc. And then I would select a subset of that data consisting of everyone who is still alive at age 80. That is called a landmark data set. Just select everyone who is still alive at age 80. And then I could simply take this sub-data set, and in the lucky situation where there's no centering, I would simply count how many of these live to be 90 years of age. That would be very simple. That would be my dynamic prediction probability. And of course, there's no such thing as an ideal world. Of course, there would be centering. If there is centering, you could estimate the probability using Kaplan-Meier instead of just simply counting. And if there's also covariates involved, you could use some slightly more complicated and incorporate them in the Cox model. But the basic idea is very simple. You take your subset, the landmark data set, and then you would do something very simple with that landmark data set. This would give you a very simple way of obtaining dynamic predictions. No need to model transitions between healthy and disabled. No need to worry about market assumption, etc. Okay, so here comes some formulas. Let's make this a little bit more concrete, or maybe to make it less concrete. Depends on whether you like formulas. The basic idea is, in more formal terms, is that you select a landmark time point. The landmark time point is called S, and that's a given age, for instance. And then you construct a corresponding landmark data set. That's by selecting all the individuals at risk at this age. So it would mean if the landmark time point is 80 years, I select everyone who is still alive at age 80. That would be my landmark data set. And then you define, that's also according to the landmark principle, you define the value of any time-dependent covariates depending on the value they have at the landmark time point. So you evaluate any time-dependent covariate at this age S. So I would simply count everyone who is age 80. I would simply keep track on whether at that time the person is disabled, yes or no. And that would be my time-dependent covariate. It would no longer be time-independent. It would be fixed at the current value of the landmark time. And then you could fit a simple Cox model. And there is a lot of S's and T's, but this is just to say that this is the current value of the predictors, and the value of your regression coefficients will then, of course, also depend on the particular selection of the landmark data. There's another thing that I will discuss in a little while. It's not really necessary, but it has some advantages too. If you have a certain horizon in mind, for instance, 10 years later, to censor everyone 10 years later and not use for about later. Okay, if you do that, you will obtain estimates of the regression coefficients, that what the Cox model will give you, and also estimates of the baseline hazards. And then for a new patient, formulas would maybe a bit complicated, but for a new patient with certain values of the covariate, what you would do is to calculate the linear predictor for that individual, multiply it with the baseline hazard, and that will give you the hazard specific to that individual at that time point. And given that hazard, you could calculate the corresponding survival probability. So the whole thing amounts to fitting a Cox model. So I was first selecting some data, making a selection of your data, fitting a Cox model, and using that Cox model for your dynamic prediction. So there are two things to remark here. First of all, because of the S's and T's floating around, you might not notice this, but this is actually the Z is time fixed. It's the value of a time-dependent covariate, but the value is fixed at one time point, so it's not a time-dependent covariate. The value is taken as fixed in one landmark analysis. Also, the beta S is also not time varying. It might be different if you select another landmark time point, but it's not time varying. It doesn't depend on T. T is actually the time, the follow-up time. So that's one thing to remark. And the other is that why do we do this administrative centering? As I said already, you don't have to do this, but sometimes it can be a good thing to do. If you enforce administrative centering at the horizon at which you do your prediction, you have a certain horizon in mind when you do a prediction. If you use administrative centering at that horizon time point, then your prediction will also be correct, also if the proportional hazards assumption does not hold. So there is some robustness that protects you from, if the proportional hazards assumption is not valid, you will still get accurate predictions. Of course, if the proportional hazards assumption does hold, you don't need to do this, and it's better if you not to do this because it will be less efficient. Okay. Yeah, so this is, if this is what you want to do, only to obtain a dynamic prediction for people aged 80, what is the probability that they will live to become 90 years of age? We're done. This is it. Very often you're in a situation that you want to have more ambitious. You want to do a dynamic prediction not only for people aged 80, but also for people aged 77.5, people aged 82.34 years of age. And then you can be a bit more ambitious and combine different landmark models to obtain what we call a supermodel. Not a supermodel in fashion, but different kind of supermodel. Okay, so this is what you do. You estimate by fitting a control, and you can do this for each landmark time point separately, but you can also combine different landmark time points. I mean, if you look at two landmark time points very close to each other, you would expect the data selection is not very different. And also the rest is probably also not very different. You would expect the models to be very similar. You would expect the regression coefficients to be quite close to each other. And you can exploit that by saying, for instance, I'm going to assume that my regression coefficients at different landmark time points follow a certain smooth function. It could be a linear function, it could also be spline, depends on whether you like splines or regretting functions or whatever. And you can exploit that. And how you do this is actually not so very difficult. You would select a number of landmark time points, and then at each of the landmark time points you would construct your landmark data set by making this selection. And you get maybe 10 or 20 landmark data sets. You put them on top of each other, you stack the landmark data sets, and you do a stratified Cox regression stratified by landmark. And that would be a correct procedure. The only thing is that you use the data of the same patients repeatedly. If a patient can be in one or two or three or maybe all of the landmark data sets, can be present in both of them. And then that means that you underestimate your standard error to optimistic values. And for that you can use what are called sandwich estimators. This is actually, to do this, I was very surprised how easy it is. To do this in R is just only adding the plus cluster ID statement. So it's very simple to do this in R. Okay. Not only can you, so this is, I will show you this, I'll illustrate this on the data I just showed you to make it more concrete. Not only can you combine the different values of the regression coefficients for different landmark time points, you can also combine the baseline hazards of the landmark regression models in a certain sense. So you could say, for instance, okay, I'm going to assume that the baseline hazards for different landmark time points are actually one common baseline hazard, and they may differ in a certain way as to what the landmark time point is. So you can also take a quadratic function for this. So they would have one baseline hazard, and the baseline hazard for a particular landmark time point would be that baseline hazard multiplied by a certain factor. Procedure is exactly the same. The only difference is that you don't use the landmark time as a stratifying variable, but as a covariant, an extra covariant, maybe with a quadratic term. Okay, so let me illustrate this with the US HRS study, the data that I just talked to you about. As I said, I want to be able to predict the probability of still being alive 10 years later for someone aged 75 up to age 90. So I'm going to use landmark time points from 75 to age 90. Those are my landmark time points. Equally spaced in 1 year intervals, so there are 16 of those. Those are the 16 landmark time points. So I have 16 landmark data sets. I put them on top of each other. And then, see, for each of these landmark time points, I construct my landmark data set, as already said. And also, I'm going to take all the people who are still at risk or still alive at that landmark time point. Compute the current value, that's according to the landmark principle, compute the current value of ADL disability, and then set the horizon at 10 years later. And then I'm going to fit a Cox model for each of these landmark time points. So here's some results. So this is the landmark data set. This is the size of the landmark data set. So you see that it's actually increasing. That the reason is that this is a sort of, when it started was just a random sample from the population, from people older than 70 years of age. Some people were already 90 years, some people were 85, etc. So that's why it actually increases as you have a higher landmark time point, because at a later age, more people were already included. And then it decreases again because the people die, of course. And then you see some of them are ADL healthy and some of them are ADL disabled. That's the top one. So here is actually, this is a graphical representation of 16 Cox models. This is the Cox model at age 75. These are the regression coefficients, and I don't know whether you can see it, but this is the confidence interval for each of the predictors. This is past smoking, current smoking, BMI, ADL disabled, gender, and education. At age 75, this is one Cox model. The regression coefficient of one Cox model. At age 90, these are the regression coefficients of another Cox model, and in between there are 40 more Cox models. This is just a graphical representation of all of the Cox models. And you see that some of the things, not much happens. They'll stay horizontal. That means that it doesn't matter whether you're 75 or whether you're 80, the effect of high school in terms of surviving another 10 years doesn't change. And for some other variables, like smoking, it's very clear that it does. So compared to the reference category is a non-smoker, compared to non-smoker, the current smoker at age 75 has a quite high regression coefficients. That means that the probability that this person will live 10 years longer is much lower. Current smoker has a much lower probability of living another 10 years compared to a non-smoker. But by the time you reach the age of 90, it doesn't really matter at all. So you can start smoking again after age 89. No, that's not really true. But anyway, so the reason is, I think, is some sort of selection. People who have managed, while smoking, to become 90 years of age, well, they will so tough. They will live for a long time, even while smoking. So, and there's also ADL disability that, no matter how old you are, will increase the probability of not surviving the next 10 years. And gender is, in a sense, is always, females have a real okay, this is the result of this supermodel. Now this is 16 separate Cox models. And what I've done here is to try to make, to make smoother pictures of these models. Most of them we see are quite horizontal, so they could maybe be replaced by one value, one value. So this is the result of actually I didn't mention this, but backward selection procedure, where we started with all quadratic interactions of the covariate and the landmark time points, and they were removed if they were not significant. So most of them you see that they will have a constant effect. That's also what you see in the pictures, more or less horizontal lines. Only smoking, there was evidence that this effect was changing over the landmark. I'll skip this. And so here you see the blue lines are the results from the supermodel and then superimposed on the previous separate Cox models. This is the result of the dynamic predictions you get. The dynamic predictions that you get from the landmark supermodels. You see here males and females. Males are the top, females on the bottom. And from left to right, you see the never smokers, the past smokers, and current smokers, and the two lines corresponding to healthy and ADL disabled. First of all, of course, the males have a lower probability everywhere than the females of living yet another 10 years at that age, certainly. Also, you see that healthy people have a higher probability compared to ADL disabled people of living another 10 years. And also you see this effect of the smoking, the current smoking. You see, compared to never smokers, at age 75, it's 60% probability for a male to live another 10 years, but only 30% for a current smoker. And by the time you're 90, you see that this is 20 or 30%, and it doesn't really matter whether you're a current smoker or not. So that is the fact that this is so changing is because of this non-constant effect of smoking. Okay, a little bit about software. Not so quickly. Yeah, I should hurry up. Okay, the advantage of the two advantages I would say of landmarking. One advantage is that it's so simple to do. You don't need to do any integration. You just need to data selection for your landmark sample. You need to select your data, and it's very easy to do this. And there is some software associated with the book that I wrote, Quantum Howling, that you can look up on the website. That makes it possible to do this. Okay, so then we are in a workshop for dynamic prediction for cancer research. So I should say something there. Now at least I'm coming to both competing risks and cancer at last. This is data from the EBMT, the European Group of Blood Marrow Transplants, for which we work together quite closely. There are two competing risks here. So people get a stem cell transplantation. They have CML patients, chronic myeloid leukemia patients. They get a stem cell transplantation usually from a different donor. Get foreign stem cell, foreign blood, and the intention is that this, to be very crudely, sorry for this, that the foreign cells kill the cancer cells of the patient. And that's if the cancer comes back, then it's called a relapse. And this is non-relapse mortality, but it also can happen that the patient dies without relapse. So these are the two competing risks: either relapse or non-relapse mortality. And you see that especially the non-relapse mortality occurs especially in the beginning of the follow-up, and relapse is more evenly spread. And the objective in general terms is to give a prognosis for a patient with a certain post-transplant history. So we know something's transplantation. The prediction is to be based on covariates, baseline covariates. I've only selected two to keep it simple: a year of stem cell transplantation and a risk score, which has already been defined. The risk score is based on age, on the gender, combination of the donor and recipient, etc. So it's based on several covariates. So there's a low, medium, and high risk, and there's one time-dependent covariate, and that's acute graft-versus-host disease. Thomas already mentioned that as well. The idea is that foreign cells kill the cancer cells, but if they do that, they sometimes also attack the healthy parts of your body, and if that happens, that's called acute graft-versus-host disease. If it happens soon, then it's called acute graft-versus-host disease. And there's either high grade or low grade. High grade is more serious than low grade. So the thing that I want to, the dynamic part is that I want to do for a patient for which I know that the patient is still alive without relapse at some time, maybe 1 year after transplantation, and other covariates. I want to know what is the probability that he or she will have a relapse within the next, I chose 5 years. What is the probability that this person will have a relapse in the next 5 years? What is the probability that this person will die without a relapse in the next 5 years? That's the things I want to know. And I want to take into account this time-varying time and covariates. Like occurrence of low-grade or high-grade acute graft-versus-host disease. Not so ambitious as what Thomas was trying to do, but still it's a time-varying covariate. I will skip this, so it only mentioned that in terms of what I want to predict the probability of having either a relapse at within some horizon, or the other event, death without relapse. And those are actually what you could call cumulative incidents, additional cumulative incidents. Additional on still having no event maybe after 1 year. What is the probability that I will have either a relapse, J equals 1, or death without relapse, J equals 2, within some time? That's what I want to do. And you could, don't look at forms, you could either explain to you how you can use landmarking in relatively simple Cox models to obtain predictions in overall survival. You can still use that same principles, all those same principles, also in the context of competing risks. You would do them for each of the core specific hazards. You would apply a landmark model, maybe a landmark supermodel, and then you can combine the two the two cost-specific hazards to obtain a cumulative guess. Formulas don't. The disadvantage, so it's possible. The only thing is that what I don't like really about it is that sort of the simplicity of the landmark is a little bit lost here, because you see the formulas quite utterly. It's not so difficult to program that. It's not so nice. And the other disadvantage that you always have in terms of prediction, that the effects of the covariate on the cause-specific hazards is not necessarily the same as the effects of covariate on the cumulative side, and that's what we are interested in. So we would be nice to have sort of a kind of a fine and gray type of model that we could use for dynamic prediction. That's sort of a fine and gray landmark model. That's the idea. This is just saying that this has been done before. Cortez and Anderson and my own PhD student Nikolai, and there's a follow-up paper by Cortez and Thomas also in 2013. So what it's worth stepping back a little bit. What in the ideal situation, the ideal situation motivated the landmark approach maybe. So you could say, what in the ideal situation where there's no censoring, what would you do? You would select people. If you suppose that you are interested in people who have been event-free for 1 year, for instance, and you want to predict what's the probability that they will have a relapse within 5 years. Okay, so then you would select people who are still at risk after 1 year. That's your landmark data set again. And then for each of these individuals, you would say, okay, this one had a relapse within 5 years, this one did not have a relapse within 5 years, this one did have a relapse, etc. So you would make 0-1 covariate variables, yes or no. Did this person experience the event of interest within the time horizon that I'm interested in? Those would be simple 0-1 covariates, outcomes, not covariates. 0-1 outcomes. And the expectation of these outcomes is exactly the probability that I'm interested in. And it's exactly the probability, the cumulative incidence, the probability of having a relapse within the next 5 years. That's the expectation of these 0-1 variables. So I could try to make a model for these expectations. For instance, a logistic regression model. That's what I would usually do there. And then relating the covariates to the probability of having events. And then that would actually be very simple. And then after obtaining the covariates, the regression coefficients, you could say then, you could say then, okay, for a new patient, this is a new patient, what would my prediction be like? I would take the same linear predictor, but then based on this new value of the covariates. And then I would put it back on the probability scale, and that would be my prediction. That would be the easiest thing to do. So a logistic regression model, and then for a new patient, I would say what is the predicted value based on that model for that patient. The disadvantage is, of course, that this is not an ideal world. We do have censoring. So we cannot simply count yes or no, 0-1s for everyone in the room who will have a relapse within the next 5 years. Yes or no. So we do have censoring, and then we have to do something special. And there's two things that you can do in this case. One is inverse probability weighting, and the other is what is very, a trick that I like very much, is pseudo-observations. So you could calculate pseudo-observations for each of the individuals, and they would, in some sense, replace the observations that you do not observe. You don't observe the 0-1 observations, but you would replace them by the pseudo-observations. And how are these defined? The only thing you need is a sort of a non-parametric overall estimator of the thing that you're interested in, so the cumulative incidence, based on your whole data set. So this is my estimate. Looks a bit odd maybe, but this is just a normal non-parametric cumulative incidence estimate based on the data that I have. And then you have, this is your overall estimate, and then you, for every individual in your data set, you leave that individual out, and you recalculate that non-parametric estimator with that observation left out. That's this thing here with the minus I. And then your pseudo-observation is the sample size times the overall estimate minus sample size minus 1, and your estimate put this in the left hand. That's the pseudo-observation. It has been introduced in survival analysis by Anderson and Klein, and it has been used also for computer risk, for sort of mimicking the final grain model. Okay, so and you could do this, and then the idea is actually very simple. Then you can, instead of, I should say something first. If there is no censoring, at all, then it's very easy to, you can check this yourself. Then it's easy to see that if there's no censoring, then your pseudo-observations will actually be the true observations. If you do this trick with this estimators, this linear combination of the estimators, if there is no censoring, it comes back exactly to what you would do otherwise if you had complete data. And it has also some nice properties without which I will not read to you, but it essentially says that you can, for all practical purposes, replace the 0 ones that you do not observe in all the in the statistical procedure by the pseudo observations and still get accurate or consistent results. So what you would do normally is you would, in the logistic regression model that you would otherwise use, would be based would be based on a certain estimating equation. This is the estimating equation. And instead of using the 0-1 variables, you would use the pseudo observations instead, and that will give you correct predictions. This slide you have already seen before, because after having fit the model, the situation is, the procedure is exactly as in the ideal case where you do not. Okay, and then you can also, I will not go into details with this, we like the supermodels very much, and you can also do sort of supermodels type of things with these pseudo observations. Okay, I think if we have, I think my time is up. I will only want to show you a little bit of results also. This is the type of things you get. Looking at relapse, these are the pseudo observations for different time points. These are histograms of the pseudo observations. You see that the majority is close to 0 and 1. Pseudo value of 0 means that this person will not have a relapse within the next 5 years. And these are the persons that will have a relapse within the next 5 years. And also similarly, these are the persons that will not have a relapse in the next 5 years after 12 months, and these will have a relapse in the next 5 years. Okay, and maybe look, so show you sort of the prediction probabilities that you would get typically. And here you see relapse, the probability of having a relapse within the next 5 years, and the probability of having non-relapse mortality, of dying without relapse in the next 5 years. You see here this is relapse, non-relapse, low risk, medium risk, high risk. You see the high risk patients have a higher probability of having both a relapse and also a higher probability of having a non-relapse mortality. And this is also the three different plots are then no acute graft-versus-host disease, low grade and high grade. This has so that the fact that it's interesting that of acute graft-versus-host disease is in such a way that the high grade decreases the risk of relapse and increases by lot the risk of non-relapse mortality. It decreases the risk of relapse. That has to do with people working in the field know this, the graft-versus-leukemia effect. Okay, some very short summing up. No proportional hazards. So I only used, this is to contrast this with the use of pseudo observations in computing risk before. What they did is they started off from time 0 and they used several pseudo observations to fit something like finding gray models. We are only using one pseudo observation for each individual, or one for each n-bar time, so not several. And so that means that we're avoiding the proportional hazards assumption. We're not using that, and in that sense it's robust against violations of that proportional hazards assumption. But it's also, of course, less efficient if the proportional hazard assumption does hold. It's quite easy to implement. That's what I like about it. And in general, discussion of advantages and disadvantages of landmarking versus standard approach. Standard approach would be like a multi-state model. There is software who are doing multi-state modeling. There's some software also for doing landmarking, but the nice thing is that you actually don't need that software. You can do it yourself. There's an advantage of the standard approach that also you gain some biological understanding hopefully by modeling reflexive probability transitions. Landmarking is more direct. It really focuses to the dynamic prediction, and it has advantages that it's simple and also robust. Disadvantages, of course, that you don't learn anything from looking in detail on transitions. That's recent things. So, thank you very much.